So I just wanted to introduce Perrine. She's a faculty member here, and prior to joining us here at Cornell in 2011, she was at NREL in Golden, Colorado, working on some alternative energy research, and that was continues as a theme in her work as she has been here at Cornell. Her PhD and MS are in mechanical engineering from Stanford, and she has an MS in aeronautical engineering from ENS and Toulouse. And so her interests are utilizing renewable liquid transport fuels, modeling the processes that go into fuel generation and combustion in these types of contexts. And with that, I'll just turn it over to Perrine and look forward to the fun.
Thank you so much for the introduction. Thank you so much for the
Oh, she also got a career award recently. I'm sorry. Yay! Hey. That's brand new information.
Thank you. I'm actually very excited to be able to talk to you. It was first time giving a talk to Cam, so hopefully I'll be able to make myself understood. So what I want to talk to you about today is something that most people don't want to hear about anymore. It's about combustion. So I say it's a love-hate relationship because when you're talking about climate change and pollution and so on, combustion is the culprit. There's no way around it. Combustion is the culprit. So we want to get rid of combustion. We want to look at solar and wind energy and not burn things anymore. But it turns out that combustion is not going anywhere anytime soon. So this is the outlook of energy sources. So it's from BP. So it might be a bit biased, but it's not, it cannot be as biased as that. So we're here, and most of our energy comes from oil, coal, and gas. A little bit comes from hydro, nuclear, and renewable, which, by the way, includes biofuels. So there's a little bit of combustion hidden in renewables. But even as we move forward, this doesn't drop dramatically all of a sudden. So combustion is here, combustion stays. So we need to be better at it. The thing is, we know how to burn fuels. We've been doing that very easily for a century or so. You can take even McDonald's oil, put it in the car, and it's going to burn, and it's going to be running. We're just not doing that fully optimally yet. So what we want to do is really push the envelope of optimal combustion. And there are ways we haven't tested yet that are promising, that would give us much better efficiency, less pollutants, and so on. But it has some drawbacks. For example, there's a lot of talk these days about low temperature combustion. Combustion typically occurs at high temperature, but if you drop the temperature a bit, you can have significant benefits for some of the pollutants, especially nitrous oxides. The problem is, when you start talking about low temperature combustion, what is combustion first? Combustion is when you take an hydrocarbon molecule, put it in the presence of an oxidizer, you let it sit a while, and then all of a sudden it goes boom, and you have combustion. You go from lowish temperature to high heat release, high temperature in your burn product, and the idea is that you capture this heat release and convert it into some type of mechanical energy. So one key parameter in any combustion system is the time it takes for your fuel mixed with oxidizer to actually go boom. That's what we call ignition delay time. In an engine, this is an especially very important parameter because it tells you when to inject your fuel in your engine to get the maximum heat release, maximum expansion, pushing on your piston to capture mechanical energy. So I'm plotting ignition delay time as function of temperature. So 1,000 over temperature. For some reason, it's easiest that way. So high temperature is here, low temperature is here. As you could expect, if you increase the temperature, you're going to ignite your mixture of fuel faster. So your ignition delay time drops dramatically. As you decrease the temperature, that's where things start to go kind of weird. So at high temperature, all the fuels burn the same way. There's no real difference between different types of molecules, fuel molecules. the delay, the change in ignition delay time is very small. As you move towards low temperature, then you can have orders of magnitude of difference depending on your fuel molecule. And the weird thing is there's this region where as you decrease the temperature, your combustion goes faster. So this is something that is not intuitive, at least from the very basic energy balance point of view. But when you start looking at the details of the combustion process itself, when you start looking at the chemistry behind it, then it all makes sense. There's some competing pathways between radicals that explains why, as you go towards low temperature, some chemical pathways take over, and they actually end up being faster. So at low temperature chemistry, at low temperature, everything is kind of fuel dependent and kind of uncertain. There's some, if you make a little bit of mistake on the temperature, then you're going to get a large difference in behavior. So that's where we operate right now. Produces a lot of NOx because it's high temperature. This is where we would love to operate because of certain type of pollutant that are reduced. But then it becomes a gigantic control problem, just because everything is fuel dependent and everything is so much changing with just little change in temperature. So again, high temperature, all fuels behave similarly, and at medium and low temperature, they are very different fuel behavior. So when we are designing an engine, more and more computational science takes a significant role. Actually, the combustion community is one of those communities leading CFD in terms of advances in development of numerical methods. But combustion is still complicated. We do not know how to simulate engines and get proper, accurate predictions for pollutants. And the reason for that is we don't know how to integrate this very diverse chemistry into our CFD. And the reason for that, I'm going to get to it in a moment. So my group, my research activities are in between chemical kinetics and CFD. We want to take whatever chemists develop in terms of chemical modeling, their understanding of this behavior, and develop the numerical methods that allows us to put that in CFD, which for now does not exist, again for a reason that I'm going to mention in a second. I'm going to assume that chemistry is not really your field, so I'm going to give you a very quick summary of what we need to know to understand chemistry in the context of combustion. So I'm in the mechanical engineering department. Typically, students and people in mechanical engineering are there because they wanted to avoid as much as possible taking any chemistry class. So chemistry is not something that we talk about in combustion, in MAE, but because of the so combustion system is historically very much anchored in MAE. This is engines, so this is pure MAE. Now that we are reaching the limits of what we can do without the chemistry, the combustion people start to look at chemistry. That's why we are bringing more and more of those type of things. But I'm not a chemist. What I am is a computational fluid scientist, and I'm taking the equations coming from the chemistry and working on them. So the equations themselves, I'm not developing them. I'm just taking them from real chemists. So here's what happens when you take a fuel and you put it with an oxidizer. What you get out of it is thermal energy and mostly carbon dioxide, water, and some pollutants. In between, you actually get a range of molecules. The most important ones are called radicals. So radicals are just very reactive species. They have a very short lifetime, and they attack everything they see. So that's those molecules are those that are accelerating the combustion process. So we describe the process from the chemical point of view as a list of elementary reactions that describe how molecules, individual molecules, actually collide with one another and convert into different species. So a chemical model is just this huge list of elementary reactions that provide which molecules collide with one another and how fast they collide and convert into reactors. And how fast is described by what we call the rate coefficient that takes the Arrhenius form. So the most important part of this term is this exponential. So there's an exponential of minus an activation energy divided by the temperature. So already you see the problem. We have an exponential dependence on the temperature, and the temperature in the combustion system varies from 300 Kelvin to 3000. So there's going to be some high dynamics involved. So from the reactions, we know that the law of mass action applies. So we can convert this list of reactions into a mathematical model that just describes the production or the consumption of concentrations of species as function of the rest. So this is a very mechanical, systematic way to look at it. There's a very systemic form to go from here to a conservation equation. So that's without looking at transport. So you're assuming that you have a box with a very well mixed fuel and oxidizer and you let it evolve. No transport whatsoever, that's an ODE. What we really want to do is solve those equations in an engine. So we need to add the space to it. So we end up with a list of PDEs that are convection, diffusion, plus reaction. So this term here gets transferred to the PDE as a source term. So what's the problem with the chemistry? There's two of them. There's more than two of them. But the first one is that even to describe the combustion of a very simple molecule, we need a lot of variables. Each variable is associated with a transport equation. So you take even the simplest fuel relevant for gasoline, for example, that's hexane. Hexane is just a 7-carbon linear chain, so very simple molecule. To describe how it converts into carbon dioxide, you need 550 equations. So ethane is just the simplest one. The most relevant ones are 12, 15, 16 carbons. So we really quickly end up with thousands of equations that we need to solve to just capture the dynamics of how the fuel is converted into products. The next issue is coming from those chemical rates. Usually what we're interested in is what happens at the end of the combustion process. Especially pollutant formation is kind of a slow process. It's about a time scale of a second. The dynamics of the resulting equations involve timescales of the order of 1 nanosecond. So if you're a computational scientist, you know that if you want to get stable and robust computational methods, you need to restrict your time step to be able to resolve the fastest dynamics. So to get to the end results where you want the actual amount of pollutant produced over 1 second, you actually need to resolve processes on a very small time scale. So it takes a lot of iterations to get to your results. That's the stiffness of the equations, and that's one of the major issues with chemical kinetics, this discrepancy of scales. And that's just for one single fuel molecule. Real fuels are combinations of hundreds of those molecules. So now we are considering a chemical model to simulate an engine and combustion in an engine. We end up with this huge kinetic description that we need to fit into our CAP code. To give you one order of magnitude, if you were to describe the chemistry very simply with one equation or a couple equations, and you go to a CFD software, and I'm giving you 1 billion grid points to map your engine and to simulate the equations, to solve the equations. The volume you would be able to resolve without any model whatsoever. So if you just take the Stokes equations, the chemistry equations, and resolve everything, the volume you would be able to simulate with 1 billion points is about 1 centimeter cube. So obviously, we are really, really far from the engine, the full engine, and that's even with a very simple chemistry. So we need simplification at every possible aspect of modeling of this engine needs simplifications. So that's where my group comes in. So we said in between the chemical kinetics and the computational fluid mechanics, we want to enable the use of detailed chemistry in the simulations of complex reactive flows with a focus on combustion. And the challenge is, as I hope I convince you, is the complexity of the combustion chemistry. So many species, extremely different time scales and length scales. So I have activities in basically a range of, so my projects span everything from chemical kinetics all the way to CFD. So I have, I'll mention it briefly at the end, some analysis of the kinetic systems themselves. I have more applied problems where I'm looking at actual reactors, trying to look at multi-phase system. And what I'm going to talk about today is more here. It's about model reduction and where we stand right now in trying to fit this huge detailed chemical kinetics into CFD using model reduction. So I'll start with one typical way we developed to simplify the chemical kinetics. So, as I mentioned, the chemical models are just a list of reactions. You can see it in another way than just a list of reactions. You can look at how the species, the chemical species, are linked together. So, if you can look at it as a network. So, if you take, for example, this methyl cyclohexane molecule, and you can draw a schematic of where the fuel goes in terms of molecules. So, methyl cyclohexane will start by losing a nitrogen, and then the cycle might open up. So that's chemistry stuff. But you end up with this kind of nice network that shows how the fuel molecule goes all the way to, it's probably not complete, the carbon dioxide and other stuff. So the objective is to simplify this network.
I'm curious, in terms of time scale, how do the times for all those reactions compared to the time it takes gas to expand through the chamber? Is it that by the time it expands all the way, we're working with byproducts, or is it that
yes, the chemistry is
is
much faster than any that most of the flow scales in the system.
So it would be a decent approximation if we say the first everything there happens and then we start thinking about that.
So it depends on the system. So you can have a regime map where you have the time scale of chemistry on one axis, the time scale of turbulence on the other time scale in the other axis. And depending on where your configuration is, you will have different types of interactions between the flow and the chemistry. Sometimes the chemistry is going to behave just like everything was very well mixed. That's easy to model because there's no interaction really. On the other side, you have the chemical timescales that are extremely fast compared to the turbulent timescales. Again, it's kind of easy to model because you can make a lot of assumptions in chemistry without compromising the accuracy. The problem is in between. And the problem with the in-between is that it's exactly the regime we want to be in if we want to push the envelope of efficiency and clean combustion. So yeah, it depends. I'll come back to this in a minute. So how are we going to simplify this network? So the first, this is the typical methods that we've been working on. The first obvious one is to look at the network and try to keep branching out. So you just cut branches and forget about all the reactions associated with those branches. And it turns out that it works well for most systems. It's very crude. The important thing is how do you know which branches you can cut without compromising on the results. But this doesn't change the framework, the mathematical representation of the chemistry. There's other methods that are more mathematical in nature that will try to combine equations with one another, that will try to rewrite the equations entirely to reduce the dimension of the system. But today I'm just going to focus on this early one, that is a species elimination. So again, we're just trying to identify any branches in this network that we can remove without changing the overall dynamics of the system. All right, so this is a method that I developed some time ago that is based on graph interpretation of the kinetic network. And it's actually now being used in a similar variant of this is used in a lot of reduction codes. So the idea is very simple. We take our network, every species becomes a vertex, and there's an edge between the vertices, provided that there's a reaction that couples the two. So, for example, species A and B are related by one reaction. And we can add a weight on those edges based on some chemical measure, in this case, some reaction rates data. So we can construct like this. We can rewrite our network as a set of vertices and edges. Each edge has a weight. And now the idea is, what species can I remove? What branch of this can I remove? The first question.
Could you help us interpret the numbers? So is it?
Oh, sorry. Yeah. So the weight here can be understood as, if I'm removing B, I'm going to do a 4% error in the prediction of A.
Of the amount of A?
Of the amount of A. Yeah. And that's so that's kind of crude, given the equation, but it works pretty nicely. If you remove B, indeed, at the end, the value of A will be reduced by something that looks like 4%.
If you remove D, what does it say about A?
That's the thing. So we have edges, so we have local interactions. We have a local quantification of the impact of species on other species. But what we want usually is formulated as, oh, I want this product predicted properly, or I want this fuel, the decomposition of this fuel predicted properly. So the fact that I have local information doesn't help me. So we rewrote this using some kind of error propagation idea. So if we want to predict A properly, I know that if I'm removing B, I'm going to do a 4% error. What about D? D is going to make a 5% error in C and a 5% error in A. So a very simple, kind of simplistic idea was to just look at the shortest path between A and D by multiplying the edges weight all the way on the way. So I would, you can replace those local information by a global information. So D, in this case, would have a 0.25% of impact on A. So we have this big network. We just have to figure out the shortest way, in a sense, from the target species, what we want to predict properly, to any given species. So it's a little bit like taking the network, grabbing the species you want to predict properly, sticking it out, and then you look at the species that are further away from this target species, and then you cut that from the mechanism. So it's kind of it appears like a crude way to simplify a complex network like this, but it turns out that it works extremely well. So for example, again, I'm back to this ignition delay time parameter. So again, the time it takes for a mixture of air and fuel to ignite. That's for isooctane. Isooctane is an important contributor to gasoline. That's what prevents knock to happen in gasoline engine. So this is ignition delay time. It's a function of temperature, and there's various things. You have the lines are the prediction from the detailed model, and the dots are the prediction from the reduced model. So we went from 850 equations to 125. So not a factor of 10, but close. And we still predict the right dynamics. With one caveat, chemical combustionists don't shy away from putting 10 decades on a graph, right? So even though my the size of my symbol is basically a factor of 2, but that's okay for the field.
Sorry, I'm still a little lost about the
Okay.
mechanism, what happened one slide ago. So, yeah, here. So when you're saying remove species with lowest coefficients, I understand how it can be a shortest path problem. And shortest path because you might have cycles, right?
Yes.
Okay. So I understand why shortest path.
So yeah.
And what are the coefficients on the nodes rather than the edges? You're finding the length of the shortest
So
path?
it's not shortest path in terms of the fewer number of reactions going from one species to another, right? It's so I'm gonna create. So this is a very simplistic graph, but I'm going to say that the distance between A and D is actually the weight of the edge. So it's going to be the multiplication of the edges, the weight of the edges that I see on the wall.
So 0.25 is the coefficient of D.
It's 5% times 5%, that's going to be the coefficient of D.
And this
So-
is, so the lowest one will be the one which impacts A the least.
Yes. So for example, if I had a reaction between B and D, that would create an edge here. I could go from A to D through B, and I would get another number, right? The lowest one, the highest one would be the one attributed to D. Because removing D would affect R, not necessarily through C, but it would affect it through B.
So generally you have some combination of the nodes which you care about, and then the coefficient for D would be how much it impacts all of them, or just one of them, or some combination of them.
So we have, it would be the highest impact on one of the targets.
One of the targets.
Yes.
So any one of the targets. That's
So we take the impact on each of the targets, take the maximum of it, and that would be the score associated, the coefficient associated with this species. So it's there's a lot of empiricism associated with it. But we had, I don't have them here, but we can show that even if it's extremely empirical and kind of out of my hands, the coefficients that you get scale very much like the error you actually obtain in predicting A in this case. So there are some characteristics of the chemical network that makes it that it works. And we are not sure exactly, the systems are usually way too complicated to really understand clearly why that's the case. Any other question? So the main, I guess the main results from this is that we have methods that take a mechanism, takes some configuration on which we're predicting combustion without transport, and manage to go from a very detailed kinetic network to a much simpler kinetic network that can predict the species properly.
Since you asked for follow-ups, you showed us the huge reduction, right, in the number of chemical species you're considering. The algorithm you talked about gives you a recipe for removing one, the least important.
Yep.
Are you going to recompute the whole thing after removing that one, or are you going to do one computation and then throw away 600 species?
So,
which were
yeah, I'm missing a lot of steps here. There's a bit more involved than that. So what I'm end up doing is that I'm removing batches of species and then recomputing the coefficients.
Okay.
That I found it was the best compromise between time and efficiency. There's also some aspects that I'm absolutely not talking about here, is that when you are looking at individual species importance or contributions, you forget that they're part of a network. So if you don't pay attention, you might end up removing species that will leave some of the species completely disconnected from the rest of the network. We can also have species that are formed but never consumed anymore. So you end up trapping mass in those intermediate species that were not important, not very important at the beginning, that were produced first and then consumed as you went through the full combustion process, that would just pop up in the reduced model. That would absolutely not be physical or chemical for that matter. So we have a lot of wrapper algorithms around that to make sure that the model we end up with is actually proper. All right, so moving on to a more CFD type things. So we have this. This is a typical example. We go from 150 to 100, kind of 100 species. 100 species, that means 100 equations on top of the Navier-Stokes equation that you want to solve in CFD. And that's typically way too many to be reasonable. So so that's, even that is not enough to be able to simulate this molecule into CFD. So we need to do something else, and what we decided to do is try to see if we could combine what's going on in CFD with what's going on in the chemistry, and design methods that sits at the CFD level that helps us reduce the complexity even more. So for this, I'm going to assume again that some of you don't have any CFD or fluid mechanics background, and I will very quickly introduce you to the concept of Large-Eddy Simulations. So this is a jet, a turbulent jet. So you have some kind of fluid injected at high velocity in a quiescent environment, and what you see developing very quickly are turbulent structures. So in CFD, this is very neatly described by the Navier-Stokes equations. So if you were to solve Navier-Stokes equations fully, you would be able to capture what's going on. So let's not talk about combustion right now, just pure fluid mechanics, non-reactive. The problem is, you would need a grid that can actually capture all the structure, the smaller structure of your turbulent field. And that typically leads to extremely fine grids that are not practical. So people have been developing for a long time very efficient techniques or modeling framework to deal with that. And the one I'm concerned about today is called the Large-Eddy Simulation. So the idea is what you care about in your simulation is not necessarily the small-scale structure. You really want to capture the energy of the flow. So, and this energy is contained in the larger structure of the flow. So you take your Navier-Stokes equations and you're going to apply a filter to them so that you kind of filter out the small scales and solve the equations in terms of variables of the large scales. That way, because the large scales are not as resolved as this, you can resolve them with a much larger grid. So that means less computational cost. So if I zoom in into my grid, so again, direct numerical simulation, a direct resolution of the Navier-Stokes equation would require my grid to be able to resolve every single structure. The LES grid is going to be much larger, but again, it's a grid. So what it means is we have one value of our variables, velocity, or in this case just velocity, pressure, density, at the center, for example, of the grid. So you can think of it, and it's kind of crude, but it's kind of visual. You can think of the value that you assign to yourself as the value you would get if you filter the field and remove all the small scales. So it represents what happens at the large scales, and the small scales are basically so the small scales are still important. They're still impacting the flow. They're still representing what's happening in terms of competition between diffusion and convection. So what happens at the small scales in LES is brought back into the equation through a closure. So the effect of the small scales are modeled and added to the equations. the nice thing about non-reactive turbulence is that the small scales, there's a very good assumption that says that they behave the same way no matter what flow you're looking at. So you can define a model for the small scales of turbulence that you can apply to any kind of turbulent flow simulation. Again, that's kind of a simplification, but the idea of the small scale being universal is key in this context of just solving for the large scales. When we're talking about combustion, it's very different because combustion occurs at the small scales. And combustion is not universal. So this idea that you can model the effect of small scales in a universal way does not apply to combustion. But still, we want to use this AES framework to solve our reactive cases. And that's where the challenge lies, because we don't have any good model for the small scale of combustion because it's not universal. It's case dependent, it's chemistry dependent, it's flow dependent. So there's been a lot of work trying to develop models that can work in certain situations and less so in other situations. But typically, the most successful models are so hard, so heavy in terms of assumptions that they apply in a very specific range of regimes. So and because of this, they cannot capture the full effect of the chemistry on the flow. So there's, for example, the most commonly used turbulent combustion model cannot be used to simulate engines because it would not capture soot formation. So we're using kind of a different framework to look at the combustion problem. That's called, so we're still in an LES framework, meaning that we're solving the filtered equations, we are solving for large scales of the system, but we are going to look at the chemistry using a Monte Carlo approach. So we are going to solve a model conservation equation for the PDF, the probability density function of the fluid properties in terms of species and energy variable using a Monte Carlo approach. So we have this weird hybrid code where we're solving the Navier-Stokes equation in the LES framework. So we are using a grid to solve Navier-Stokes equations, but the composition, the density, the local density of the fluid is going to be extracted from a Monte Carlo simulations using notional particles. So if I move on to the next slide. So those particles carry one representation of the fluid composition. So I have particles everywhere. They each have a certain composition and volume. And if I want to know the density at one of my grid cells, I'm just looking at the notional particles that are inside the cell at that time and look at the PDF that they represent. And we're moving those particles around according to stochastic differential equations, so in space and in composition space. So it's this approach, even though I'm not going very much to the details, this approach is very superior to most turbulent combustion models. For one reason, it's general. So there's no strong assumption on how the combustion occurs. And those kind of techniques are, I think, the future of turbulent combustion models, just because they're not restricted on typical simulations. Yeah.
Are the stochastic PDs not coupled between species and the field variables for the CFD?
They're coupled in a subtle way. So they're coupled through the diffusion and the density. So phi is the composition. The composition is used to extract, so composition and temperature used to extract the density that appears here. So they are coupled definitely, but not explicitly.
So also the second one, is it in ODE or is the second DT supposed to be DW?
It is an ODE. This one
It is an ODE. So this is your chemical kinetics.
this is my chemical kinetics. This is a Wheeler process, so the stochastic is more accurate here. This is one formulation of this framework, the most simplest formulation of this framework. There are others. What we end up with is, from the chemical point of view, ODE equation that represents the chemical system, so from which we can just use our chemical mechanisms to advance the composition in time. So that way we can directly use our mechanisms without any modeling assumption. So this is nice, no assumption, it's very general, and that's exactly what we want. The problem is that it's much more expensive than any other techniques, because we're still carrying a vector that has the size of the number of species kept in the mechanism, and we have, this is the chemical source term, the same one as I mentioned earlier, and this one is very expensive to compute. So we have two issues, the size of this vector and the chemical source term. So we know how to go from a detailed kinetic network to a much simpler one, but that was not enough. It's still not enough to be able to solve these LES-PDF equations. So now we look at the CFD and try to see if we can do something else. So this is a typical flame that we simulate with whatever simulations techniques. This shows the temperature. We are injecting some fuel here, some hot co-flow to stabilize the flame, and the rest is basically air that is being injected at low velocity. So we have this flame developing, and it's very easy to realize that whatever happens here is, in terms of chemistry, is extremely different from what's going to happen here. Here you have the fuel that is just starting to decompose. Over there, you start having the soot formation processes that kicks in those long-term, long time scales, behaviors, dynamics that happen. So the chemistry that you need here is actually very different from the chemistry that you need here. And from that matter, whatever you have on both sides is basically no chemistry. You don't need any chemistry to describe a cold flow. So the idea is, rather than simplifying the network for the entire flame, we'll try to simplify it for this region, or this region, or this region. And we're going to try to adapt the number of equations we're solving in our CFD to what we actually need to solve in the CFD. Yes?
Can I ask maybe what's a silly question, but in terms of the interaction between the CFD and the chemistry, are the scales that you use ever comparable to the size of the molecules? Like, can you really think of it as fluid flow, or is it kind of particulate granulate flow at any of the scales that you use?
We are in CFD, so that requires the Nusselt number to be large enough. We are definitely way above the continuum limits.
Okay.
So the chemical model represents an average behavior of some volume.
Okay.
We are
so
in the
even
continuum.
things like you were saying at the far end of the flame, like soot particles and stuff like that.
So soot precursors. I'm not going into the description of the formation of solid particles.
Okay.
So I'm still at. I'm stopping. If you know a little bit soot formation, I'm stopping at about 4 aromatic rings together. So it's large, extremely large molecules, but not large enough to be considered as a soot particle.
Particles.
So we can add. We had option to add this extra step where we actually creating solid particles and then tracking the number density and the size. But we are not talking about this, because the chemistry model for those processes is completely different. So, yes, I'm taking way more time, but I stopped. So the idea is, rather than using a single model for everything, we're going to try to be smart about the model we're using. So we start with a full composition and a detailed mechanism, and we're going to switch from space to composition space, where the axes are basically the species concentrations. So there's no link anymore with the physical domain. But in this composition space, we know that depending on where you are, the type of chemistry going on is going to be extremely different. if you are in a region of the composition space that basically describes air, there's not going to be any chemistry. So we want to decompose our composition space into regions. Those regions are going to be characterized by involving a certain type of chemistry, a certain part of my chemical network. And then for each of those regions, I'm going to try to figure out how to best represent my chemistry. So that means describing the composition by a much reduced vector. We just want to carry the species that are important for the region, and a reduced mechanism. So same kind of idea of model reduction that I described before. So that when I go back to my simulation, where I have to follow what's going on with each of those particles. So each particle carries its own composition. It's evolving according to the chemical mechanism. So typical behavior, I start with my composition phi. I want to see what's the composition after delta t, so I'm just integrating my detailed model until I reach delta t. This means using the full mechanism. I don't want to do that. So instead, I'm going to try to figure out where my particle lies in composition space, finding the region it belongs to. Once I know where it belongs to, then I know that the proper representation is a much smaller vector, and the proper mechanism is a much smaller mechanism. So I'm going to remove my full vector and just use a reduced representation for it. So I'm gaining a lot in terms of memory and storage. And I'm going to advance this composition in time, not with a full mechanism, but with my very much reduced mechanism that just describes the part of the network that is relevant in this region. So obviously, doing that, I'm going to introduce some error. So the way I'm doing it is I don't want to figure that out on the fly. That would be much too expensive. So I want to pre-compute, to pre-evaluate, predetermine all my mechanisms beforehand. So for that, I assemble a representative sample of every composition that I might see in my flame simulation. So I can do that easily with some kind of a stochastic reactor simulation. So once I have a good sample of my composition space, I can start looking at how I want to put my regions so that samples in the same regions behave the same way, so are associated with the same chemistry. The way we do that is very systematic, so I'm going to go quickly through it. But we basically define a measure of the kinetic homogeneity, meaning that if this value is high, it means that my samples are very different in terms of the chemistry they involve. If it's low, it means that they are very similar. And that's where there's chemistry kicks in. Two particles that are very close in composition space can be very different in terms of the chemistry they involve, because there might be small changes in some of those very reactive species that I mentioned at the beginning, called radicals. Small changes in those radicals typically will switch your dynamics in different paths.
So can I ask a quick question? The
Yeah.
PDF you showed of Monte Carlo the particles from the samples of Monte Carlo approach, they looked correlated very much. So
they are correlated, but with some, there's still significant variance.
Okay.
So for example, you see in here, you're going to see a lot of variance. So yes, there's some correlation, but it's not perfect. There's still a lot of variance. So the goal is to put my regions so that I keep together the samples that behave the same way, have the same chemistry. So we do that as a minimization problem, where we start by separating those samples into two groups, and then we take each group and we start to separate them into two other groups, so that doing so, we are isolated pocket of particles that will be associated with the same chemistry. All right, so I'm skipping somewhat of the details. So this is an example. I start with my composition space. It's 2D, and I'm just going to put hyperplanes through my composition space to isolate my samples into regions where the chemistry is going to be the same. And I'm going to store that in a binary tree. So this structure, again, it's just a cutting plane algorithm. It's very efficiently stored in terms of a binary structure. So I can very easily figure out in which region a particle is by going through a tree. All right, so, and then once I have defined my regions, then I can define my reduced model for each of the regions by applying the exact same algorithm that I showed you earlier, just on the compositions that are within the region. That way I can focus on the part of the network that is important for this combustion space region. So I'm going to skip that. So it turns out that it's a method that is pretty efficient. To give you an idea of how efficient that is, we took the worst case possible, where it's like solving for a flame, but removing the transport. So we have micro mixing, but everything, the large scale are homogeneous. So we are solving this stochastic type reactor, and we're solving it, we're looking at the number of equations we need to solve it as function of the error we are introducing by using reduced model. So if we are using the detailed model, we are going to have no error and or a full set of equations. So I'm going to be at 1. Then if I'm applying my reduction model and I'm considering only one region, this is the graph I'm getting. So again, as I start removing species, I'm going to introduce error, and that describes that error. So as I decrease the number of species kept in the mechanism, then I'm increasing the error. The blue one is what we get when we have this multiple regions set up. So when we are completely adaptive, we actually have multiple models that apply to specific regions of the combustion space. For a given error level, it turns out that we can decrease the number of species by a factor of 3. So by doing adaptive, I indeed accomplished exactly what I wanted. I removed entirely my chemistry where I didn't need it, and because I gained computational CPU time there, I can afford more details elsewhere, so I can create less error elsewhere. So we applied that to LES, an actual LES PDF simulation. So this is a flame colored by temperature. So again, you have the fuel, the cool fuel injected with hot air to stabilize the flame. The rest is cold air, and we see the temperature starting to rise, and after a while, everything is burning. So this is the temperature field, and this is the same field, but now colored based on the set of equations that are used locally. So every color corresponds to a different set of equations. The light blue corresponds to a model that has no chemistry whatsoever. And indeed, that exactly corresponds to the co-flow of air, where there's no fuel, there's no chemistry, everything is cold. So we don't need a chemical model. So we're actually solving the Navier-Stokes equation with constant density. So we're gaining a lot of time here. And as I go towards the higher temperature regions, then we start seeing different models appearing that describe the light yellow here might describe the post-combustion behavior, where you have the slow oxidation of carbon monoxide into carbon dioxide. All right, so that's just a summary of the talk. So we are looking at bringing more chemistry into CFD, and we are doing that both at the chemistry level, trying to produce reduced order models, and at the CFD level, where we're trying to combine knowledge of the flow with more advanced techniques to reduce the cost and simulations. And the key aspect of this that we started looking at is how we control the errors. Right now, a lot of those algorithms are empirical, and there's no guarantee at all that we're going to get a result that falls below a certain level of error. So we cannot control error for now. All right, so I'm just going to put that here. Moving forward, we're looking at fuel design. So in those systems, we are part of a national effort called the Colloquium program, that try to figure out how to optimize at the same time the fuel and the engine. So until now, you had 3 types of fuels: gasoline, diesel, and kerosene. And you had 3 types of engines to go for each type of fuel. And the engines were trying to optimize the engines for a specific type of fuel. Now we are in a world where we know how to convert biomass to a multiple of hydrocarbon fuel. So we have access to new types of molecules that we can burn in our engines. So the idea is to take a step back and see if there's any way we could try to find a fuel blend, and a completely redesigned engine, so that we would get much better combustion profiles. So we are trying to look at how we can, by blending molecules, we can design chemical models and use chemical models CFD to show that we have benefits in combining certain molecules. All right, I'll stop there. Thank you so much for your attention. Sorry I took too long.
Professor Pepiot is visiting NMAE. The graduate students are coming today, so maybe one quick question, if we have time for one quick question.
When you talk about design directions, is there some parameters that people need to figure out? Like, is it the shape of an engine or something else?
So it's more than that. It's also how you achieve combustion. So if you take gasoline, you achieve combustion by sparking a plug. If you take diesel, you achieve combustion by compressing your air so that it becomes hot, and then you're injecting your fuel, and you're relying on auto ignition. So there are different methods you can achieve combustion. So it's not necessarily due to the shape of the engine, it's more what combustion regime you want to achieve. So they're talking about hybrids between this gasoline and diesel, because both of them have benefits and both of them have disadvantages. So they're trying to figure out how to take only the benefits of those technologies and bringing them together. So it's more on the how do you achieve combustion machines.
Thanks, Perrine.
So if you want to stop by in my office anytime, I'd be happy to talk to you.